Who was Oppenheimer and what did he do before building the bomb? A look at some of the early work of J. Robert Oppenheimer from the conversation, the man known as the father of the atomic bomb. The release of the film Oppenheimer, July 2023, has renewed interest in the enigmatic scientist J. Robert Oppenheimer's life. While Oppenheimer will always be recognized as the father of the atomic bomb, his early contributions to quantum mechanics formed the bedrock of modern quantum chemistry. His work still informs how scientists think about the structure of molecules today. Early on in the film, preeminent scientific figures of the time, including Nobel laureates Werner Heisenberg and Ernst Lawrence, compliment the young Oppenheimer on his groundbreaking work on molecules. As a physical chemist, Oppenheimer's work on molecular quantum mechanics plays a major role in both my teaching and my research, says the writer. The Born-Oppenheimer approximation. In 1927, Oppenheimer published a paper called On the Quantum Theory of Molecules with his research advisor Max Born. This paper outlined what is commonly referred to as the Born-Oppenheimer approximation. While the name credits both Oppenheimer and his advisor, most historians recognize that the theory is mostly Oppenheimer's work. The Born-Oppenheimer approximation offers a way to simplify the complex problem of describing molecules at the atomic level. Imagine you want to calculate the optimum molecular structure, chemical bonding patterns, and physical properties of a molecule using quantum mechanics. You would start by defining the position and motion of all the atomic nuclei and electrons and calculating the important charge attractions and repulsions occurring between these particles in the molecule. Calculating the properties of molecules gets even more complicated at the quantum level, where particles have wave-like properties and scientists cannot pinpoint their exact position. Instead, particles like electrons must be described by a wave function. A wave function describes the electron's probability of being in a certain region of space. Determining this wave function and the corresponding energies of the molecule is what's known as solving the molecular Schrödinger equation. Unfortunately, this equation cannot be solved exactly for even the simplest possible molecule, H2, that's hydrogen, which consists of 3 particles, 2 hydrogen nuclei or protons and 1 electron. Oppenheimer's approach provided a means to obtain an approximate solution. He observed the atomic nuclei are significantly heavier than electrons, with a single proton being nearly 2,000 times more massive than an electron. This means nuclei move much slower than electrons, so scientists can think of them as stationary objects while solving the Schrödinger equation solely for the electrons. This method reduces the complexity of the calculation and enables scientists to determine the molecule's wave function with relative ease. This approximation may seem like a minor adjustment, but the Born-Oppenheimer approximation goes far beyond just simplifying quantum mechanics calculations on molecules. It actually shapes how chemists view molecules and chemical reactions. When scientists visualize molecules, we usually think of them as a set of fixed nuclei with shared electrons that move between nuclei. In chemistry class, students typically build ball and stick models using rigid nuclei as balls and sharing electrons through a bonding framework with sticks. These models are a direct consequence of the Born-Oppenheimer approximation. The Born-Oppenheimer approximation also influences how scientists think about chemical reactions. During a chemical reaction, atomic nuclei are not stationary, they rearrange and they move. Electron interactions guide the nuclei's movements by forming an energy surface, which the nuclei can move on throughout the reaction. And in this way, electrons drive the molecule's progression through a chemical reaction. Oppenheimer demonstrated that the way electrons behave is the essence of chemistry as a science. Computational quantum chemistry. In the century since the publication of the Born-Oppenheimer approximation, scientists have vastly improved their ability to calculate the chemical structure and reactivity of molecules. This field, known as a computational quantum chemistry, has grown exponentially with the widespread availability of faster, more powerful, high-end computational sources. Currently, chemists use computational quantum chemistry for various applications, ranging from discovering novel pharmaceuticals to designing better photovoltaics before even trying to produce them in the lab. At the core of much of this field of research is the Born-Oppenheimer approximation. Despite its many uses, the Born-Oppenheimer approximation is not perfect. For example, the approximation often breaks down in light-driven chemical reactions, such as the chemical reaction that allows animals to see light. Chemists are investigating workarounds for these cases. Nevertheless, the application of quantum chemistry made possible by the Born-Oppenheimer approximation will continue to expand and improve. In the future, a new era of quantum computers could make computational quantum chemistry even more robust by performing faster computations on increasingly large molecular systems. This is by Aaron W. Harrison, Assistant Professor of Chemistry, Austin College. We publish from the Conversation on the Creative Commons, and this is on Unexplained Mysteries. Please leave your comments, and thank you for your support. Support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.